Welcome back. And we saw Taylor series representation for functions and Maclaurin series representation for some functions. And we saw some examples. How to write sin x as a power series, as Maclaurin series, and how to write cosine x as Maclaurin series, and how to find the radius of convergence for all of them. Now we'll try one more example. Find the Maclaurin series representation for x cosine x. The Maclaurin series is written as f of x equal to the sigma version will be nth derivative at 0 over factorial n times x to the power n, and the expanded version is f at 0 plus f prime 0 over factorial 1 x f double prime 0 over factorial 2 x squared, and so on. This is the expanded version. Now, in step 2, because we have done elaborately the representation for cosine x in the earlier problem, we will take that representation. So, x cosine x is the given problem here, f of x equal to x times cosine x. You can write this as x times sigma. The cosine x representation from the earlier problem is that, from earlier one, negative 1 to the power n, x to the power 2n over 2n factorial. Because we know that this representation this part is the Maclaurin series for cosine x from the earlier example. So now f of x equal to x cosine x, which is, if I take this x inside the sigma, I can write this as sigma n varying from 0 through infinity, negative 1 to the power n, x to the power 2n plus 1, because there is already an x to the power 2n and there is an x outside, can combine and say it is x to the power 2n plus 1 over factorial 2n. Just the way we did the radius of convergence, you can find the radius of convergence by applying the ratio test. So we are going to continue with this section. Just the last part of this section is about binomial series. It's a very popular series. You have already been using this. The only thing is you may not know this as a series. If k is any real number and absolute x is less than 1, then 1 plus x to the power k is sigma. We will get to this notation in a bit. It is Maclaurin series representation, by the way. It is 1 plus kx plus k times k minus 1 over factorial 2x square, k times k minus 1, k minus 2 over factorial 3x cube, and so on. If I write the generic representation, generic term, I will write this as k times k minus 1 times k minus 2, and so on, k minus n minus 1, which will be k minus n plus 1, divided by factorial n, x to the power n, and it goes on and on. So this particular representation This particular representation actually refers to this coefficient here. So writing 1 plus x to the power k in Maclaurin series representation like this for absolute x less than 1 is named as a binomial series. So let's find out how we get this representation 1 plus x to the power k. So let's start with the Maclaurin series representation of this function. We know that f of x equal to f at 0 plus f prime 0 over factorial 1. You know that Maclaurin series is always centered at 0. And f double prime 0 over factorial 2 x square. The generic term is going to be nth derivative at 0 over factorial n x to the power n, and so on. What is f of x here? F of x is given to be 1 plus x to the power k. So 1 plus x to the power k, if I write this whole thing in sigma notation, it is sigma n varying from 0 to infinity. The nth derivative of f at 0 over n factorial times x to the power n. All right, now step 2, we will evaluate these coefficients. So evaluate the values nth derivative at 0. So first let's start with f of x, which is 1 plus x to the power k. So f at 0 is going to be just 1 to the power k. Then the first derivative, it's k 1 plus x to the power k minus 1. So the first derivative at 0 would be just k times 1, so it is k. Then the second derivative is k times k minus 1 times 1 plus x to the power k minus 2. So the second derivative at 0 is going to be k times k minus 1. So if you continue that, so you will have the third derivative at 0 is at x. This is x and the other one is 0. So it is at the x, if you compute, it's k minus 1, then k minus 2 times 1 plus x to the power k minus 3. Then third derivative at 0 would be k minus 1, k minus 2 times 1. So it goes on like this. So if you have to write the nth derivative, notice one thing, when you are doing the third derivative, you get 3 factors. When you do the second derivative, you get 2 factors. For the third derivative, it ends at 2, k minus 1 less than 3. For second derivative, it ends at 1, k minus 1 short of 2. So nth derivative at the x is going to be, if I follow the same technique, it's going to have n factors. So it goes on and down. Where will I end it? For 3, I end at 2. For n, I will end at n minus 1. And 1 plus x to the power k minus n. So if I expand this, it is k minus 1, k minus 2. These are all products. You have k minus n plus 1 1 plus x to the power k minus n. When you do nth derivative at 0, you're just going to have k, k minus 1, k minus 2, up to k minus n plus 1. So if I substitute all of this as we normally do, substitute these table values into step 1, you get f of x, in this case, which is 1 plus x to the power k, will be sigma n varying from 0 through infinity, nth derivative at 0 over factorial n times x to the power n, which will be sigma n varying from 0 through infinity. We will substitute for nth derivative at 0 that we had evaluated is k times k minus 1, k minus 2, etc. up to k minus n plus 1 over factorial n times x to the power n. So this big representation, we write this one as sigma n varying from 0 through infinity, k chosen n. This is the notation we use, x to the power n. This notation is a combination of n things out of k things. It can also be written as k, k, c, n. Sometimes the calculator uses this symbol. It's combination of n things out of k things, or selecting n things out of k things. So it's a topic from permutations and combinations. So the representation that we have written here is a representation for this particular one. In short, it can be written like this. Now, we have got the Maclaurin series representation. Now, the next step, we have to actually find out the radius of convergence, where this series converges. So, finding radius of convergence, which is by ratio test. So now you do an plus 1 over an, which is k, k minus 1, k minus 2, up to k minus n, because now we are increasing by 1. And 1 before that is going to be this, up to k minus n, divided by n plus 1 factorial. Then I'm going to divide that by an. So flip and multiply by factorial n divided by k, k minus 1, k minus 2, up to k minus n plus 1. And then we have x to the power of n plus 1 over here. Over here, x to the power n. So some of the terms are going to get cancelled out. So all of this is getting cancelled out with this. The usual trick, if you apply here, it is n factorial times n plus 1. Also, you're going to have x to the n getting cancelled out with x to the power n plus 1, giving you just x. N factorial cancel out. So you are left with just absolute x over absolute x times k minus n, absolute of that, divided by n plus 1. This is all with absolute sign here. If we take the limit as n approaching infinity, so before we do so, we just rewrite this and write this as 1 minus k over n divided by 1 plus 1 over n. You can also write this as k over n minus 1, because we are allowing n to approach infinity. We want to divide the numerator and the denominator by n. So we do that. As we do not know the nature of k, we are using absolute, but denominator is n plus 1, so it's always positive. Now you allow n to approach infinity. Which will be limit as n approaching infinity of absolute x times k over n minus 1 absolute divided by 1 plus 1 over n. You know that this approaches 0, this approaches 0. So you are just going to get absolute x here. As we are applying ratio test, whenever this absolute x less than 1, the series converges. So this tells us that by ratio test, the binomial series converges written as the representation that we mentioned. It is KCN, or in the expanded form k minus 1, etc. k minus n plus 1 over factorial n times x to the power n. Another representation is k n in parentheses, which is n chosen out of k, 1 plus x to the power n converges whenever absolute x is less than 1. It converges whenever absolute x is less than 1, and it diverges for all other values. So this is binomial theorem. We'll do a simple example based off this binomial theorem, which actually, it's very familiar to you, but we are going to use to understand how binomial series is expanded using this formula, using this particular formula. So let's expand 1 plus x the whole square, which is not a big deal. We know all of us know what this value is going to be. If we apply binomial series, do we get the same thing is the question. So let's write the step 1. So f of x, which is written as 1 plus x to the power k. Normally, if it is k, we write like f at 0, f prime 0 over factorial 1, and so on. In this notation of binomial, we are going to write this as sigma n varying from 0 through infinity, k n chosen out of k, x to the power n. So in our problem, it is n varying from 0 through infinity. K in this problem is 2. So we write 2 n x to the power n. So we have to expand this. So when we write this in this expanded form, we are going to plug in to at 0, it is 2, 0, 0 items chosen out of 2, chosen 0 out of 2, x to the power 0, 2 chosen 1, 1 chosen out of 2, x to the power 1, 2 chosen out of 2, x square. If that doesn't make sense to continue here, it will mean 3 chosen out of 2, which is incorrect. So the rest of the terms will become 0 here. The convention is that k, 0 chosen out of k is always assumed to be 1. So you have 1 x to the power 0, which is 1 also. In order to do 2c1, you have to use this formula. So k times k minus 1 up to k minus n plus 1. So you have to start off at 2, start reducing. So you have to have only one factor. So 1 chosen out of 2 is just 2. So it's 2x plus 2 chosen out of 2. So the way you do that, it's 2. Of course, you'll have here 1 factorial, but 1 factorial is equal to 1. So what is 2c2 or 2 things chosen out of 2? It is 2 times 1 less 2 minus 1, which is 1, divided by factorial 2 x squared. Even if you do 2 out of 3, 3 chosen out of 2, how do you reduce? It is 2 times 1 times 0 divided by factorial 3. So all after 3 out of 2 and after, all of the terms are going to be 0. That is 1 plus 2x plus x squared. Don't we all know that 1 plus x the whole square equal to 1 plus 2x plus x square by FOIL method or by binomial method? So it is agrees with what we have learned earlier. The binomial theorem method is this. It converges when absolute x less than 1.